In this video, we'll talk about the first derivative test for analyzing critical points. The point of this test is to figure out if a critical point is a local max or a local minimum without needing to plug in values, because that can't really tell you what's actually going on. The point is to figure out sort of what the graph of the function looks like around these points so we can get into ideas of curve sketching, as well as determining sort of what things look like near this point. So let's think more generally about if I have a graph of a function and I have a critical point, how do I get a local maximum? So say I have a point on my graph that's here, and that's going to be a local maximum. Well, what does that mean? Well, that means in some sense I have to sort of come up to the value on the left, hit the maximum, and then fall away after that. Right? I have to go up to hit the max and then come down afterwards so that I don't end up getting bigger beyond that point. It could happen like this. It could also happen something like this, where I have a point like this, I come up to the maximum, and then I fall away after it. In the first case here, my derivative is 0. In the second case, my derivative does not exist. But this is really the only way that I can get a maximum. I have to sort of go up to hit the max, and then go down afterwards. Basically, I have to have the case where my function is increasing to the left of my critical point and decreasing to the right. That happens for the other case as well. But how can I talk about increasing and decreasing functions? We saw in the previous video that this could come down to the derivative. What really happens here is I need f prime to be positive to the left of my critical point, and I need f prime being negative to the right. This gives me a maximum. If you want to think about getting a local minimum, you just reverse these. Right? To have a local minimum, I need to decrease to the critical point and then increase after it. So decrease to the left, increase to the right gives me a local minimum. And that idea right there leads us to the first derivative test for finding and classifying critical points of functions. What's the idea of this test? So let's suppose we have a critical point C for our function, and that f is differentiable near C, with possibly the exception of not being differentiable at C. Right? If I have a corner or a cusp for a critical point, that's going to be a place where it's not differentiable, but I can still apply this test to it as long as everywhere nearby is still fine. Then what happens? So case 1, if f prime goes from positive to negative, moving from left to right across C, then f attains a local maximum at C. This is exactly what we talked about before. If it's positive to negative, that means going increasing to the critical point and then decreasing after it, that's a local maximum. If it goes from negative to positive, then I get a local minimum. And then the third option here is f prime does not change sign across C, i.e. goes positive positive or negative negative. In that case, I do not get a local max or a local min at C. So I get neither a max or a local min if I don't change sign across that point. This might be a case where, like, my function goes increasing, critical point increasing. There's a critical point there, but it's not a local max or local min because it's not the biggest or smallest around it. You might think of something like f of x equals x cubed here as your sort of standard option for what this might look like. The example we want to solve here is to analyze the critical points of this function, 2x plus 1 over x squared plus 1. So first we have to find the critical points, and we do that by taking the derivative. So it's my derivative here. Well, I can find that by the quotient rule. And then I can expand and simplify out this expression. Now and look for points where this either doesn't exist or equals 0. What exists everywhere because of a polynomial on top, polynomial on the bottom, and the bottom's never 0, right? X squared plus 1 is never 0, so it exists everywhere. So I can set this to 0. And setting this to 0 is equivalent to setting the numerator equal to 0, because the fraction can't be 0 unless the top is 0. Setting to 0, I get 2 minus 2x minus 2x squared equals 0. I can divide through by 2 and flip the sign. X squared plus x minus 1 equals 0. This unfortunately doesn't factor, but I can choose a quadratic formula. My roots are at x equals negative 1 plus or minus the square root of 1 plus 4 over 2, negative 1 plus or minus root 5 over 2. Now with this, I can draw a number line to figure out what's going on here. So now we have two zeros at minus 1 minus root 5 over 2, and minus 1 plus root 5 over 2. And I want to plug in to figure out what's going on here. I can either plug in numbers, or I can use the fact that I know what this function looks like. If I go back to my derivative, the bottom part here is always positive. The top part is a parabola facing downward. Right? If I just look at just the numerator by itself, it's a parabola facing downward. So that means that the signs of this function will follow the signs of that parabola, which is facing downward is plus in the middle and minus on the two outsides. So I'll get plus, minus, minus here. I can also plug in numbers. So if I say plug in 0, because 0 falls between these two values, because root 5 is bigger than 1. If I plug in 0, I get a 2 over 1, so that's positive. If I plug in something like 5, because it's definitely bigger than the outside, I'll get a negative number, and if I plug in something like negative 5 as well, I'll also get a negative number there. That'll give me these signs here as well. So what does this tell me? Well, this tells me that this critical point here goes minus to plus, that's a local minimum. And this critical point over here goes plus to minus, that's a local maximum. This here tells me that x equals negative 1 plus root 5 over 2 is a local max, and x equals minus 1 minus root 5 over 2 is a local min. So that's the first derivative test and the idea of how we can use it to figure out whether critical points are local max, local mins without having to graph the function or really know too much what's going on, as long as we can figure out where these derivatives are 0 and whether they're positive or negative on the opposite sides of these critical points.